ஸோ இன்னைக்கு என்ன பண்ண போறேன்னா fuck. I really don't know. Like, okay. ஃபேனை போட்டு மாட்டோமா? சரி. ஸோ இன்னைக்கு வந்து same with the linear algebra. I'm not going off track, I promise. Linear algebra and maybe some Bayesian probability. Sorry about that. Okay. Let's go. What am I waiting for? Ooh, look at me. Handsome. I'm chopped. Yeah, I thought of doing this yesterday and it all fucked up. Luckily, the pen is back. Look at that. The pen is back. Oh, let me take a quick piss break before anything. What should I do? This one. This one. Boom. Boom. Bap. Bada bap bo. Pow. I think we kind of went through all of this. All the bases. Okay, I think I kinda understand this basis. Yesterday we went on a deep rabbit hole on basis, but it's like I want to visualize it. How does it actually look? Give me a, let's ask, 3x3 matrix with all its bases for me to copy and paste. But the thing is, when I go in GeoGebra, brother, look at this. How am I gonna go here? Go to the 3D. Geometry? No. 3D calculator. Stupid ass name. Where is it? Should I have a vector? Okay, we have the matrix and we have Nothing happens. Nothing happens, bro. Standard basis of 9 of them. You have a diagonal thing going on. Oh wait, why is this thing? Why is 0 0 0 0 a thing? Oh, what the fuck? Makes no sense. Yeah, this is what I'm talking about. This is the symmetric matrix. Basic symmetric 3x3 matrix, 6 of them. Meaning, let's say or a 3x3 surface எடுத்துப்போம். Right. When we plot the basis for all of this, this will be like inga one, in the direction one, in the direction one, in the direction one, in the direction one, mala, in the side la. So if we count them up, 1, 2, 3, 4, 5, 6, we have 6 bases. Basic skew symmetric 3x3. So what do you mean skew? Yeah, whatever, bro. Standard basis for all 3, but how is it 9 of them instead of? Oh, I kind of get it. If you like look at this way. Question mark. Great question. When we talk about bases for 3x3 matrices, the number of element base is equal to the number of spaces. Different. Oh, it just like multiplies. That's what does it mean? What is it? Symmetric 3x3 matrix. What's the difference between 6? I just had a really good memory, childhood memory. I was thinking about something else. Okay, whatever. Stand over. Symmetric. Oh, it's just like a. Fuck, it's cold. My leg's getting cold. Okay, it spans all the spaces in the 3x3 matrix. What does it actually mean? What does it actually look like? Let's see, standard basis, symmetric basis. I understand standard symmetric basis. But let's go here.
Alright,
oh, this one. Yeah.
Have the direction being 1 for pillars that we can use back steps forwards in the y direction. And then the 2 means we're taking 2 steps on this a hat and k hat.
Yeah, understand. Okay, standard basis from the symmetric basis. Meaning symmetric basis spans only, so let's say நம்ம ஒரு matrix ஒரு 3-dimensional space ஒரு 3-dimensional space இருக்கு, and they want us to just span this area, so that will be like a 3x3 matrix, right? So if we take all of the bases on this one, right, all of the bases will squish into in these kind of directions. So all of them will like squish into these kind of directions and make it possible. But On the contrary end, if we go to a standard basis, they're just talking about the entire span, meaning the entire fuck. Entire three-dimensional, entirety of all of this. That will mean this plus this. That's 1. We need to add. That's 6 plus 1. This plus this. Right. And another 1, obviously. And this plus this. So it's a combination of 2, right? Combinations of 1 plus combinations of 2 for the entire span. If we were to calculate the entire span of things, that will mathematically mean 1 0 0 0 0 0 0 0 0, and the next one will be relatively easy to see. This will be this one. The next one will be 1 over here, and so on. So that's the idea behind basis, and basis changing to another basis.
I think only 3 of them do. This one is symmetric. This last one is symmetric.
Oh yeah, that's the idea of symmetric. In a standard, this is not symmetric because it's not symmetric. So if we'll actually plot it on, right? The first one will span here, right? Where will the second one? Oh fuck! I need an actual. I don't actually understand it. Fuck. Hello, got a places to be. Oh shit. I didn't. Fuck. Sorry. Sorry. Just. Oops. Oopsie. Whatever. Fuck. Thank God I looked at it though. Yeah, if you guys didn't know what happened, I just forgot to change from this to this. Look at how beautiful it is. Ooh, yeah, I'll just have to add a fade. I gotta show them. I'm a Christ follower. Whatever. I fucked up the couple of shit. It is what it is, bro. Can it create a video? I really like this app, GPT. I don't know what they fed it. They probably fed some fucking mathematics books. That's actually crazy though. You could just like feed like books and call it to a GPT or some shit. I mean, it's crazy. The only issue is it costs a lot of GPU spaces. You gotta be careful with it. Fuck.
Welcome to our video on elementary matrices. Today we're going to learn about a special type of matrix called an elementary matrix with a focus on one. Elementary matrices are special matrices that are obtained. Now, let's introduce our specific elementary matrix.
Okay. What the fuck are you talking about? For now, we'll just go with the flow. We don't have to. We don't have to have a deep understanding. That's fucking annoying. So wait. I think I got it wrong. Fuck. So in a 3x3 space, the base is symmetric. Fuck. Symmetric shit would be this one, this one, this one, right? And it's a combination of twos. So this one and this one, okay, and this one and this one, or this one or this one. This happens whenever we span on this side, right? Now imagine we go the entire three-dimensional span. Dot. What happens now? Now it's like we can go this one, this one, this one, and wait. No. What does this mean? Oh, it's just like a we have one combinations of one, 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 combinations of one. Why? How is it 9 though? Makes wait. What is going on? Joe Rogan. I think I'm a little bit retarded. Okay, we have 6. I can understand we can have 6, but where does all of the other shit comes from? You know, where does this one? What does it mean? Does it mean I don't know. What does it mean? What does this mean? What does this mean? What does this mean? What does anything ever mean? I'm so smart. But like what the fuck? Does it mean somewhere in the center? I mean, that doesn't make any sense. Okay, let's just like move on.
And the one in the middle with a 1 in that position, in the 2 position, would be symmetric. But so I've got 3 of these original 9 are symmetric. But so this is an example where but that's not all, right? What's the dimension? Let's put the dimensions down. Dimension of M was
Mhm.
9. What's the dimension of, so we call this S, is what? What's the dimension of this? I'm sort of taking simple examples where we can spot the answer to these questions. So how many, if I have a symmetric, think of all symmetric matrices as a subspace,
6.
how many parameters do I choose in 3 by 3 symmetric matrices? 6, right. If I choose the diagonal, that's 3, and the 3 entries above the diagonal, then I know what the 3 entries below. So the dimension
Yep.
is 6.
Yep. Talk it,
I
talk.
guess what's the dimension
Talk
of
it, talk,
this?
Unc.
Let's call this space U for upper triangular. So what's the dimension of that space for upper triangular? 3 by
2.
3. Again
3.
6.
Oh, wait, what?
Again 6.
What?
And
Upper triangle. Let's look at 6 for let's look at it. I see where the mix-up might be. Careful, I'm back. Upper triangle. Upper triangle is basically this shit. I can change this, change this, change this, this one, this one, this one. I mean, mathematically it makes sense, but it's like I just want to visualize it. Can I make it visualize it? Finally. Why is this a 4 by 4 matrix? I want a 3 by 3. Okay. What is this, bro? Bro, what the fuck is that? Give me a 3 by 3 matrix, ka. Monkey. What happens if I add the 4th dimension? Whoa. I don't know what that is. What is this? It's a true 3 by 3 matrices. Matrices? What the fuck did I even say? Okay, I don't know what it means. Let's do 2 by 2. Okay, that is a bad website. Bro. Look at that. That's actually... Bro, look at that. When the t goes to 0. So you can like find... Can you find zeros? What will this be called? அந்த ஆரஞ்சு கலர் இருக்க vectors வந்து if you look at it closely, when the determinant is 0 and the space inside it is 0, it doesn't actually like change anything, just like kinda அப்படியே இங்கே வருது, அப்படியே அந்த சைடில் இப்படி போயிடுது. இது வந்து அப்படியே இப்படி வருது, அந்த சைடில் இப்படி போயிடுது. ஆனால் மற்ற வெக்டர்ஸ்லாம் இந்த ப்ளூ கலர் இருக்கிறதும் வெக்டர்ஸ் தான். பட் ஆனால் அந்த வெக்டர்ஸ் எல்லாம் பார்த்தீங்கன்னா அது அப்படியே பொசிஷன் மாறுது, சைஸ் மாறுது, எல்லாம் மாறுது. பட் ஆனால் இது மாறாது. இந்த வெக்டார் வந்து ஒரு இமேஜினரி லைன் பேசிக்கலி. Okay, that's actually a usable website. Upon melancholy plastic tree, are you here with me? Well, you can. Okay, I think this is just a scale. Okay, we have a 3x3 matrices. If I go oh, look at that. My boy got squished. Okay. So what happens when I do this? Oh shit. Yo. Look at him. Look at my boy. He's getting stretched. Shit. Bro. You know what I'm saying? Yeah, this could be anything though. Yeah, this is just enough. So let's take what happens. He's getting squished into 2D. Okay. His 3D features are getting squished into 2D. So you can like see him from behind too. Like this one will make him a line. Yo, look at him. Yo, Hirambe, if you can hear me, please save me. Hirambe, if you can hear me, please save me. Okay, this is a line. So this is like one basis, I guess. No, this is not a basis. What the fuck? What is going on? Oh, okay, I understand it. Okay. Kinda. Okay, this is 0. This is 1. Oh. I think I get it. So, it doesn't matter. Instead of... okay, I can fucking get it, bro. Now I can... Okay. So, the reason for this is... So, இந்த டாப் மேட்ரிக்ஸில் பார்த்தீங்கன்னா தெரியும் இருக்கும், இங்கே மட்டும்தான் 1 இருக்குது, மீதி எல்லாம் 0. ஓகே, that means what is happening below the hood is இந்த மாதிரி ஒரு 3D இது இருக்கா ஓகே இங்கே வரையலாம் it used to be like this shitty angle rotate இதுக்கு முன்னாடி இந்த மாதிரி fuck இந்த மாதிரி இருந்திருக்கு ஓகே பட் ஆனால் இந்த டிரான்ஸ்ஃபர்மேஷன் நம்ம பண்ணும்போது என்ன ஆகுதுன்னா ஃபர்ஸ்ட் இங்கே இருக்க லெட்ஸ் இங்கே இருக்கிறது ஒன்றா இருக்குன்னு வச்சுக்கோங்க எக்ஸ் இந்த எக்ஸ் கேப் ஐ ஹேட்டில் இருக்கிற இது வந்து அப்படியே இங்கே போயிடுது இந்த சைடு ஒன்றுக்கு அப்படியே போயிடுது ஓகே ஐம் சாரி fuck what am I talking I hat இங்கே இருக்கு ஓகே okay this is actually ridiculous okay இந்த மாதிரி 3-dimensional space இருக்கு okay let's completely draw the entire span why not startingல எப்படி இருக்கும் when x is 0 okay when these two are 0 when x is 1 this will happen right இங்க இருக்குது அப்படியே இப்படி ட்ரான்ஸ்ஃபார்ம் ஆயிரும் fuck sake இங்க இருக்கிறது அப்படியே இங்க ட்ரான்ஸ்ஃபர் ஆயிரும் ஓகே so that's the first thing second thing is so this will be a symmetric basis okay this will be the இது வந்து இப்போ y axis ல span ஆகும் yeah whatever okay again y x y z all the fucking same bro it's all the same okay இது வந்து vertical ல இப்போ span ஆகும் okay இது வந்து horizontal again it's all relative you know it's all fucking relative but what happens instead of இங்கேயும் இப்போ 1 இருந்துச்சுன்னா again nothing changes maybe the size increases because I don't know why quite honestly but it is what it is you know it is what it is maybe the size increase because it's all like uneven surface right ஆமாம் ஏன்னா சைஸ் இன்க்ரீஸ் ஆகிறது வந்து பார்த்திங்கன்னா இந்த சைடில் இருக்க பிளைன் வந்து இதோட பெருசாக இருக்கிறதுனால இது இப்படி ஸ்குவிஷ் ஆகும்போது இந்த சைடில் இப்படி ஸ்குவிஷ் ஆகும்போது கொஞ்சோண்டு ஹைட் ஏறுது ஸோ தட்ஸ் த ரீசன் பிஹைண்ட் எதுக்கு சைஸ் அதிகமாகுதுன்னு பட் அகெயின் நம்ம இப்போ இங்கே போட்டாலும் இது வந்து ஒரு 2D மேட்ரிக்ஸா இல்லை what the fuck why is it diagonal why is this shit it looks like JFK got shot you know what I mean it's like yo they probably used one of these like I'm telling you man look at this is like a fucking JFK documentary this is how president got shot yeah okay whatever why is it it's twice but let's just say oh this kind of stuff yeah it's just basically in the side in the what's that movie's name எந்திரன் படத்தில் பார்த்தீங்கன்னா சித்தி ரோபோட் வந்து தலையில் நைஸாக அப்படியாச்சு உடப்பா பார்த்தீங்களா அதான் இங்கே நடந்துருக்குங்க இப்போ இந்த சைட்லேயும் நான் ஸ்பேன் பண்ணேன்னா I'll get a 3D oh shit it actually rotates too that's interesting அதான் அப்படி கழுத்து அப்படி திருகி அப்படி ஒன்று போட்டிருக்காப்ல அப்படி ஆயிடுச்சு. So yeah, I think the way you like do it kinda, it's, I have a theory. Still, okay, I need to like visualize it though. Like we need to actually visualize what's going on. That's important. This will be the normal thing, I guess. But I have another theory. What if it's 1, 1, 0? What am I getting? Jeez. See what I'm trying to say? I don't know. This one. ஸோ இங்கே பார்த்தீங்கன்னா அப்படியே இது கிளாக் வைஸாக இது நான் 1 இப்படி இருக்கு. செகண்ட் இதில் பார்த்தீங்கன்னா 1 இந்த 1 எதுவுமே இங்கே காலம்லேயோ ரோலையோ இது டச் ஆகலை பாருங்கள். ஸோ தஸ் இது சுடக்கு பசில் மாதிரி போலக்கு. இந்த காலையில் சந்திரன் இதில் படிப்போம்ல, சுடக்கோ மாதிரி போலக்குது. ஓகே, ஸோ ஐ திங்க் இந்த 1 நான் இங்கே மூவ் பண்ணனா it will have the same effect. It will rotate. So that's how actually rotation in a 3-dimensional space works. Interesting. We'll keep this site handy. Go back to this shit. Yeah, this is like really cool shit too, determinant. Although I won't be using eigenvectors and 2D matrices for a while, but it's fun. It's really fun. It's getting exciting. It's getting exciting, boy.
But we haven't seen a well, actually, maybe we have got a basis here for the upper triangulars. I guess 6 of these guys.
Okay, what is an upper triangle? What is a... I need to make a coffee really quick. Give me a example. I could just make it myself, but let's all make it 1 upper triangle. 1, 1, 1, 1, 0. So, why does it look retarded? Who knows? I trust your cough. Oh shit. Give me a second. almost fucking up. Getting overzealous over here. No way. So what's so special about this upper triangle? What's so special? Just looks retarded. What's so special about it? Kind of like makes a cool pattern too if you look at it. இங்க பாத்தீங்கன்னா இந்த upper triangle பாத்தீங்கன்னா it makes like a this kind of shape too. You know what I mean? Like you guys seeing the vision. You know what I mean? Like obviously it has 6 bases, just like anything. It's obvious because I don't know why. Why is it? Why? Who knows? Fucking dipshit. Let's go.
1, 2, 3, 4, and a couple more. Make the upper triangular. So there's an accidental case where the big basis contains in it a basis for the subset. But the symmetric guy didn't have.
What happens? Interesting question. What happens when I go doink, doink? It'll go into a line. Huh. Bro, wait. Does it make a difference? No? Why is it? What the fuck does that even mean? Well, what does it mean? What does this line even mean? Does it even mean anything? Huh. Whatever.
Symmetric guy, the basis, so you see what? A basis is the basis for the big space. We generally need to think it all over again to get a basis for the subspace. And then how do I get other subspaces? Well, we spoke before about the subspace, the symmetric.
Yeah, I gotta speed it up. You're talking slow, old man.
And
Gotta fasten up.
proper triangle. This is symmetric and
Hey. Symmetric.
upper triangle.
That'll be 12 dimension.
What's the
Nah, not actually 12 dimension. Just 9 dimension. Simple, am I right? So simple. Just 9 dimension.
dimension of that
Huh.
space? Well, what's in that space? So if a matrix is symmetric and also
Oh, wait. It's actually 3 dimension.
triangular, that makes it diagonal. So this is the same as the diagonal matrices. Diagonal 3 by 3. And the dimension of this, of S intersect U, right? You're okay with that symbol? That's the vectors that are in both S and U. And that's D. So S intersect U is the diagonal. And the dimension of the diagonal
Yep.
matrices is 3. And we've got a basis, no problem. Okay, as I write that, I think, okay, what about putting together, this is like, this intersection is taking all the vectors that are in both,
Uh-huh.
that are symmetric and also upper triangle. Now,
Uh-huh.
we look
Talking
at
Tom.
the union. Suppose I take the matrices that are symmetric or upper triangle. Why was that no good? So why am I not interested in the union? Putting together those two.
Yeah, it's just like a 9-dimensional
So
space.
these are matrices that
I feel so smart.
Well,
I mean-
both, so the diagonals included. But what's that about the union? It's not a subspace. It's like taking a couple of lines in a plane and stopping there.
Oh,
line.
it's not 9-dimensional.
So there's a 3-dimensional subspace
I'm
of
wrong.
a 9-dimensional space. There's six. There's a 6-dimensional subspace of a 9-dimensional space. There's another one. But they're headed in different directions. So we can't just put them together. We have to fill in. So that's what we do. To get this bigger space that I'll write with a plus sign, this is combinations of things in S and things in U. Okay, so that's the final space I'm going to introduce. I have a couple of subspaces. I can take their intersection, and now I'm interested in not their union, but their sum. So this is the intersection, and this will be their sum. So what do I need for a subspace here? I take anything in S plus anything in U. I don't just take things that are in S, and also separately things that are in U. This is the sum of any element of S, that is any symmetric matrix, plus any element of U. Okay, now, as long as we've got an example here, tell me what we get. If I take every symmetric matrix, take all symmetric matrices and add them to all upper triangular matrices, then I've got a whole lot of matrices, and it is a subspace. And it's a vector space, and what vector space would I have? Any idea? What matrices can I get out of a symmetric plus an upper triangle? I can get any. I get all matrices. I get all.
Yeah, that's what I'm 9. Yeah, 9-dimensional space. Yeah, that's what I'm trying to say.
So it's worth thinking about that. It's just like stretch your mind a little, to think of these subspaces and what their intersection is and what their sum is. And now, can I give you a little? Well, let's figure out the dimension. So what's the dimension of S plus U in this
It's
example
9.
is 9, because we got all 3 by 3. So the original symmetric space had dimension 6.
Shit.
And the original upper triangular space.
I get it, got it.
had dimension 6. And actually, I'm seeing here a nice formula. That the dimension of S plus the dimension of U, if I have two subspaces, the dimension of one plus the dimension of the other equals the dimension of their intersection plus the dimension of their sum. 6 plus 6 is 3 plus 9.
What?
It's kind of satisfying that these natural sums
Whoa. Yo. So we have dimension of standard, no, symmetric matrix 6 plus dimension of U. The fuck does that even mean? The fuck does it even mean? Dimension of U, what is U? The U is upper triangle. Is equal to 6? No, it's not. Oh, I can't understand what they're trying to say. Okay, 6 plus 6.
equals
They got like two fucking equal marks. Makes no sense.
the dimension of their intersection plus the dimension of their sum. 6
Bro, could you like write it in a different board or something?
plus 6
I know you're the leading expert in this field, but I could do better. Come on.
is
I would do way better. Like, come on, bro. This is like easy shit for me.
it's kind of satisfying that these
I wanna see how it's satisfying. This is equal to this. How? Who said so? Dimension of intersection of these two, right? And the union. I get it. The intersection and the summation. Okay, the dimension of the intersection. Bro, I sound like a fucking geek. It is what it is. The dimension of the intersection is equal to 3. The dimension of the summation is 9. That is actually equal to the dimension plus the dimension of that. Interesting.
plus the dimension of U. If I have two subspaces, the dimension of one
So how does it work for a 4x4? Let's do for a 4x4. Fuck, nah, bro. 4x4 would be like, let's give it a try. Giving it a try. Fuck, where's my pen? A 4x4 would be. No. Fuck. Fuck no. Yeah. Okay. The dimension of summation of upper triangle and that one would be 14 because that can covers the entire span. Okay. And the union it will be 4. So that should be equal to the singular weight. I think it will be 8. Right, because ding 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 ding, shing shing shing, shing, shing 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 shing. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And the dimension of upper triangle. It will also be 8, but why? I know why. Because this thing right there. Oh, it's such a useful tool, man. Such a useful tool. And I go upper triangle. Wait, what? The dimension is the same. It's the same, you know. It's that will be 8. Okay.
What's the dimension of the other equals the dimension of their intersection plus the dimension of their sum. 6 plus 6 is 3 plus 9. It's kind of satisfying that these natural operations, and this is it actually, this is the set of natural things to do with subspaces, that the dimensions come out in a good way. Okay, maybe I'll take just one more example of a vector space that doesn't have vectors in it. It's say take some differential equation. So this is one more new vector.
Differential equations. I need to write it. Whatever. Some of it is getting connected to different. Fuck. Where was my pen? Fuck. Man. Why am I the owner of pens that don't work? I want to kill myself. Fuck. Please. Can I end it? Can I just end it? Okay, I got it. Hey, I'm happy.
Space that we'll give just a few minutes to. Suppose I have a differential equation like d second y dx squared plus y equals 0. Okay. I'm
Yes, sir.
solutions for that equation. So what are the solutions to that equation? Y equals cos x is a solution. Y
Is it? Bro, my differential is off the fucking wall. What am I even looking at? Like, what the fuck?
sin x is a solution.
What the fuck is this?
Y equals, well, e
I do know like cos x and sin x has these like wavy function. It like does one of these. You know what I mean? But yeah, that's about it. I think y. What am I? I'm looking at x squared, right? X squared does one of the. X squared does this, right? No. What am I confusing it with? So this doesn't get differentiated. So when it goes to this side. Allah Akbar, bro. Allah Akbar. May God bless me.
the ix is a solution if you want. If if you allow me to put that in. Oh, but why should I put that in? It's already there. You see, I'm really looking at the null space. I'm looking at the null space of a differential equation. That's the solution space. And describe the solution space, all solutions
He does it again.
to this differential equation. So the equation is y double prime plus y equals 0. Cosine is a solution, sine is a solution. Now tell me all the solutions. There. So I don't need e to the ix. Forget that. What are all the complete solutions? Is what? A combination.
Yeah, combination.
The solution is y equals some multiple of the cosine plus some multiple of the
Yeah, obviously, bro. Obviously, I thought of it. Yeah, obviously.
That's a vector space. What's
What?
the dimension of that space? What's the basis for that space? Okay, let me ask you a basis first. If I take the set of solutions for that second order differential equation, there it is, those are the solutions. What's the basis for that space?
Oh shit. Yo. So he's coming to say Cn is the dimension of that space. Oh, bro, that's crazy.
Now remember, what question am I asking? Because if you know the question I'm asking, you'll see the answer. A basis means all
Oh, n. The n and
things
Cn.
in the space are combinations of these basis sets. Well, this is a basis. Sin x, cos x, there is a basis. Those two,
Oh, the number is that,
they're like,
but I don't know the actual basis.
right? We have special solutions to
Those will be the basis, obviously.
ax equals b. Now we've got special solutions to differential equations. Sorry, we have special solutions to ax equals 0. I just spoke. The special solution.
What? A special solution to this? Okay. Whatever, Unc. Talk your talk.
If we're for the null space, just as here we're talking about the null space. You see that here is those two, and what's the dimension of the solution space? Is
Cn.
how many vectors in this basis? 2. The sine and cosine. Are those the only basis for the space? By no means. E to the ix and e to the minus ix would be another basis. Lots of bases. But you see that really what a course in linear differential equations is about is finding a basis for the solution. The dimension of the solution space will always be.
Oh, some motherfucker opened the coke. Fucking dumbass. I'll whoop your ass.
Will be 2.
Bitch ass motherfucker. Opening a coke. When the goat speaks, you listen.
Like there's 1803 and
Pussy ass.
of 1806 is enough to take care of 1806. Okay. So that's one more example, and of course the point of the example is these things don't look like vectors. They
Mhm.
look like functions. But we
Yep.
can call them vectors. Because we can add
I mean, sine x. I could do it. You know what I mean? No one is stopping me from doing this. This is the eigenvector, right? Huh. Bro, whoever made this, thank you so much. Kind of cleared up a lot of
and
things.
we can multiply by constants, so we can take linear combinations. That's all we have to be allowed to do. So that's really why this idea of linear algebra and basis and dimension and so on plays a wider role than our constant discussion of
Bro, ChatGPT is gonna like make everyone so smart. It's crazy. It's actually crazy. That's why I wanna work with them.
okay, that's what I wanted to say about that topic. Now,
Yo, Sam Altman. Call me. Just saying.
number
Just saying, bro.
did with matrices to go back to that number is the rank.
Just saying, Unc.
And the rank,
Listen,
what do we know about the rank?
I'll put the Christ in the ChatGPT, man.
We know it's not bigger than m, and it's not bigger than n. But I'd like
Okay,
to
what am I
is
looking
the
at?
rank. And
I'm thinking of jokes. I'm
the
like,
rank, what do we know about the rank? Well, we know it's not bigger than m, and it's not bigger than n. So, but I'd like to have a little discussion on the rank. maybe I'll put that here. So I'm picking up this
Mhm.
topic of rank 1 matrices.
Okay, yeah, this is rank 1. Small world graphs. What is it? Okay, if the rank is 0, right? It's yeah, if the rank is 0, it just gets squished into another shit. So the rank is 1. Like completely 1. It's just like a line. Like, what are we gonna do with it? Obviously, like, yeah, it's it gets bigger because it's getting. If you can think, when someone is getting, if I'm getting squished by a bro, this used to be like one of my biggest fears. You know, one of those like road rollers back in the days, and when I used to like think, what if I get caught in it? You know what I mean? What if I get squished into like a paper? What if I look like this? You know, it's like, bro, crazy on my face. But when I get squished like that, my size of me will increase. I wouldn't be this big. I would be actually bigger. That's what's happening when I squish into the shit. That's what's happening here. That's why it's this thing is bigger than the actual monkey. Not talking about black people, by the way.
And the reason I'm interested in rank 1 matrices is that they ought to be simple. If the rank is only 1, the matrix can't get away from it. So, for example, let me create a rank 1 matrix. Okay, suppose it's 2 by 3.
Yep.
And let me give you the first row. What's in the second row be? Tell me a possible.
0, 0, 0.
For this matrix to have rank 1. A possible second row is 2, 8, 10. The second row is
Yeah.
a multiple of the first row.
Yeah. Multiple.
It's not independent.
Makes sense.
So tell me a basis for that. Oh yeah, sorry to keep bringing up these same questions. After the quiz I'll stop. But for now, tell me a
Okay.
basis for
I don't want to feel dumb. The guy actually also said 0, 0, 0. So
a possible second row is 2, 8, 10. The second row is
he said 0, 0, 0. I'm not dumb.
a multiple
He's
of
dumb.
the first row. It's not independent. So tell me a basis for that. Oh yeah, sorry to keep bringing up these same questions. After the quiz I'll stop. But for now, tell me a basis for the row space. The basis for the row space of that matrix is the first row, right? The first row, 1, 2,
Yeah.
5.
First row.
A basis for the column space of this matrix is what's the dimension of the column space?
2.
The dimension of the column space is also 1, right? Because it's also
Oh, 1.
the
Yeah.
dimension.
Yeah, 1, obviously.
Of the column space
Obviously.
equals the dimension of the column space of the transpose, which is the row space of A. Okay, and in this case, it's 1. R is 1. And sure enough, all the other columns are multiples of that column. Now, there ought to be a nice way to see that, and here it is. I can write that matrix as its pivot column, 1, 2, times its times 1, 4, 5. A column times a row. 1 column times 1 row gives me a matrix, right? If I multiply a column by a row, that's 2 by 1 matrix times a 1 by 3 matrix, and the result of the multiplication is 2 by 3.
2 by 3.
And it comes out right. So what I wanted, my point is that rank 1 matrices.
Bro, the way that I'm studying right now is much more fun. I ain't even gonna lie, bro. I want to do this stream every fucking day. It's crazy. It's like I would never thought linear algebra would be fun to like learn. Honestly, man.
Every rank 1 matrix has the form sum column times sum row.
Yep.
So U is a column vector, V is a column vector, but I make it into a row by putting in V transpose. So that's the complete picture of rank 1 matrix. Would be interested in rank 1 matrices. You'll find,
Let's
their
sneeze.
determinants, that'll be easy. Their eigenvalues, that'll be interesting. Rank 1 matrices are like the building blocks for all matrices. And actually, maybe you can guess. And if I took any matrix, a 5 by 17 matrix of rank 4,
She, bro. She.
then it seems pretty likely, and it's true, that I could break that 5 by 17 matrix down as a combination of rank 1 matrix. And probably how many of those would I need? If I have a 5 by 17 matrix of rank 4, I'll need 4.
4, yeah.
Four
Makes
rank
sense.
1 matrices. So the rank 1 matrices are the building blocks. And
Oh shit, that's where all the compression. That's where all the image compression, when you like download some shit from zip, right? It is all compressed. The games we download from illegal websites, it's all compressed. That's where it's come from. It's all matrices under the hood. Who would have thought? It's all linear algebra, man. It's all linear algebra. It's all linear algebra. Who would have thought?
I can produce every rank 4 matrix out of 4 rank 1 matrix. Okay, that brings me to a question, of course. Would the rank 4 matrices form a subspace? Think
Yeah.
about 5 by 17 matrices and think about rank 4 matrices, the subset of rank 4 matrices. I'll write this down. You see,
They will.
because I'm asking the kind of questions that are short enough, but that bring out, do you know what these words mean? So I think
Quiz.
my matrix space N now is all 5 by 17 matrices.
Yep. It's a big ass
And now
matrix though.
the question I ask is subset of, of rank 4 matrix.
Rank 4.
Is
Yes,
that
sir.
a subspace?
Yep.
If I add a matrix of, so if I multiply a matrix of rank 4 by a rank 4 or less, because I have to let the 0 matrix, it's going to be a subspace. But that doesn't, just because the 0 matrix.
It is a subspace.
So the question really comes down to, if I add 2 rank 4 matrices, is the sum rank 4?
No.
What do you-
Add. Yeah, if you add it, yeah.
No, not usually.
What?
Not usually.
Oh, not usually. What do you mean by that? So let's say I have a rank 4 matrices and I add it with another rank 4. Add, not multiply. Oh, sometimes it get like, oh no. Let's say I have a -1 here. -1, -1, -1, -1. என்னம்மா என்னம்மா வேணும்? டிஸ்டர்ப் பண்ணாதீங்கம்மா. அம்மா டிஸ்டர்ப் பண்ணாதீங்கம்மா. வராதீங்க, உள்ள வராதீங்க. என்ன? Okay.
Rank 4 matrices, the sum is probably, what could I say about the sum? Well, actually, the rank could be 5. It's a general fact, actually, that the rank of
No, the rank could be -3. Checking the battery.
A plus B can't be more than rank of A plus the rank of B. So this would say if I added 2 of those, the rank couldn't be larger than 8. But I know actually the rank couldn't be as large as 8 anyway. How big could the rank be? For the rank of a matrix in M could be as large as 5. Right. So they're all sort of natural ideas. So rank 4 matrices or rank 1 matrices, let me change that to rank 1. Let me take the subset of rank 1 matrices. Is that a vector space? If I add a rank 1 matrix to a rank 1 matrix, no, it's most likely going to have rank 2. So I'll just make that one, not a subset.
Why rank 2? Let's see. Doesn't make sense. Like, why will it? If it's all 0 in the bottom, why will it increase? Why will it be? Makes no sense. On guard, bro. Makes no sense. Here's a clean 2x2 rank 1 matrices with a sum. It's not rank 1. What the fuck? Both have rank 1? No, don't. It doesn't. It doesn't have rank 1. It doesn't. What the fuck are you talking? How is that rank 1? Okay. It's not rank 1.
Okay. Okay, those are topics that I wanted to just fill out the
What? Rank 1? What? Why is the column zeros instead of that? Oh, it's the same thing, but it's like do the rows. Yeah, it makes sense, but it's like row 0 is the convention, isn't it? How? How? That is not the rank. That is not the rank. Okay, makes sense. Okay, makes sense. Yeah. Yeah, it makes sense, bro. It doesn't strictly have to be, let's say, yeah, it doesn't have to be, again, this is like without an example. It doesn't strictly have to be this way. You could like the equals will be 1, 2, 3. The rank is bigger now. Okay. Okay.
the previous lectures. I'll ask one more subspace question, a more likely example. Suppose I'm in. Let me put this example on a new one. Suppose I'm in R4. So my typical vector in R4 has 4 components: V1, V2, V3, and V4. Suppose I take the subspace
I need a quick break. How long have I been streaming? Quick little chat with my mom. Okay. Quick little chat with my mom. Oh shit, what happened to my camera? So yeah. What should I do? Should I like turn it back? Okay. Hopefully. Yeah, if the battery runs out though. I gotta check on the battery now and then. Fuck. Such a headache. 69. Good number. Funny number. Ha ha ha. Yeah, it's alright. Got a Jesus piece. is really good because I can actually, yeah, bro. So why did I stream before? So easy. Just set it up, stream. I didn't have, bro. I'm just like plagiarizing that shit. I mean, like, look at how much shit that I'm using. It's getting squished into 3D. Okay. This 3D features are getting squished into 3D. You can like see it from behind. This one will make my line. Yo, look at him. Yo, Hirambe. If you can hear me, please save me. Hirambe, if you can hear me, please save me. Okay, this is the line. So this is like one big piece, I guess. No, this is not. Yeah, okay. It is what it is, bro. It's kind of cringe looking back. This is like what? An hour before. Wait till I turn 30 years old. All of this is gonna be cringe. Whatever.
Consider that bunch of vectors. Is it a subspace, first of all? It is a subspace. It is a subspace. How do we see that? It is a subspace. Normally I could check. If I have one vector with whose components add to 0 and I multiply that vector by 6, the components still add to 0. That's 6 times 0. If I have a couple, a b and a w, and I add them, the components still add to 0. Okay, it's a subspace. What's the dimension of that space and what's the basis of that space? So you see how I can just describe a space, and we can ask for the dimension at the basis first, and the dimension, of course the dimension is the one that's easy to tell me in a single word. What's the dimension of our subspace S here? And the basis. So tell me some vectors in it. Well, I'm going to ask you again to guess the dimension. Again, I think I heard it. 3. The dimension is 3. Now, how does this connect to our single? That's the basis first, and the dimension. Of course, the dimension is the one that's easy to tell me in a single word. What's the dimension of our subspace S? And the basis. Tell me some vectors in it. Well, I'm going to ask you again to guess the dimension. Again, I think I heard it. 3. The dimension is 3. Now, how does this connect to our AX equals 0? Is this the null space or something? Is that the null space of a matrix? And then we can look at the matrix and we know everything about those subspaces. This is the null space.
Uh-huh.
What matrix?
Column
What's the matrix
space.
where the null space is then AB equals 0? So I want this equation to be AB equals 0. B is now the vector. And what's the matrix that we're seeing there? It's the matrix of 4. You see that if I look at AB equals 0, so this matrix A, I multiply by B, and I get this requirement that the components add to 0. So I'm really, when I speak about S, I'm speaking about the null space of that matrix. Okay, let's just say we've got a matrix now, we want its null space. Well, tell me its rank first. The rank of that matrix is 1, okay? So R is 1. What's the general formula for the dimension of the null space? The dimension of the null space of a matrix is, in general, an m by n matrix of rank R. How many independent guys in the null space? N minus R, right? N minus R. And this
Yep.
N is 4 columns. The rank is 1, so the null space is 3 dimensional. So, of course, you can see it in this case, but you can also see it here in our systematic way of dealing with the 4 fundamental subspaces of a matrix. So what are all 4 subspaces then? The row space is clear. The row space is in R4. Yeah, can we take the 4 fundamental subspaces of this matrix? Let's just kill this example. The row space is 1 dimensional. It's all multiples of that is 3 dimensions. Oh, you better give me a basis for the null space. So what's the basis for the null space? The special solution. To find the special solutions, I look for the free variables. The free variables here are, there's the pivot. The free variables are 2, 3, and 4. So the basis for f will be, I'm expecting 3 vectors, 3 special solutions. I give the value 1 to that free variable, and what's the pivot variable if this is going to be a vector in F? Minus 1. Now the row adds the entries add to 0. The second special solution has a 1 in the second free variable, and again a minus 1 makes it right. The third one has a 1 in the third free variable, and again a minus 1 makes it right. That's my answer. That's the answer I would be looking for.
Mm-hmm.
A basis for the subspace S, you would just list 3 vectors, and those would be the natural 3 vectors, not the only possible 3.
Okay.
Those are the special 3. Okay, tell me about
At
the
least not
column
bad.
space. What's the column space of this matrix? A.
Bro, I don't want to get over this. I don't like this.
So the column space is a subspace of R1. Because n is only 1. The columns only have 1 component. So the column space of F, the column space A, is somewhere in the space R1. We only have these columns are sorted. And
This is the go again tying back to the shit that he taught us. So this will be the row space, column space, null space of it. So the column space is basically the row space transpose. That's my understanding, of course.
what is the column space actually? Just talking with these words, what I'm doing. The column space for that matrix is R.
R transpose.
The
Oh.
column space for that matrix is all multiples of that column. And all multiples give you all of R1. And what's the remaining fourth space? The null space of a transpose is what? So we transpose A.
Null space of A1.
We
Who
look
knows?
for combinations of the
N minus R.
Gives 0 for A transpose, and the only combination of these rows to give the 0 row is the 0 combination. Okay, so let's just check dimensions. The null space has dimension 3. The row space has dimension what? 3 plus 1 is 4. The column space has dimension
I want to get
1.
over this, man.
What's the
I don't
dimension
like
of
this.
Like smallest possible space. What's the dimension of 0 space? It's a subspace.
No dimension.
What else could it be? I mean, we have
Yeah.
to take a reasonable answer, and the only reasonable answer is 0. So 1 plus 0 gives this was n, the number of columns, and this is m, the number of rows. And let me just say again, then, the subspace that has only that one point, that point is 0 dimensional, of course. And the basis is empty. If the dimension is 0, there shouldn't be anybody in the basis. So the basis of that smallest subspace is the empty set. And the number of members in the empty set is 0, so that's the dimension. Okay, good. Now, I have just 5 minutes to tell you about, well, actually about this is now the last topic of small world graph, and leads into a lecture about graph and linear algebra. But let me tell you that
Oh, bro.
in these last minutes, the graph...
Yo, let's go.
It's the graph where, so what is a graph? Better tell you that first. Okay, what's a graph? Okay, this isn't calculus. I'm not thinking of like some sine curve. The word graph is used in a completely different way. It's a set of a bunch of nodes. And
Shit. Edges, nodes, and edges.
edges
Let's
connect.
go.
So I have nodes like 5 nodes, and edges, I'll put in some edges. I could include them all. Let me put in a couple more. There's a graph with 5 nodes and 1, 2, 3, 4, 5, 6 edges.
6 edges and 5
some
nodes.
5 by 6 matrix is going to tell us everything about that graph. To be me leave that matrix the next time and tell you about the question I'm interested in. Suppose the graph doesn't have the 5 nodes, but suppose every person in this room is a node.
Yo.
And suppose there's an edge between 2 nodes if those 2 people are friends. So have I described the graph? It's a pretty big graph, 100 nodes, and I don't know how many edges are in there. There's an edge if you're friends. So that's the graph for this class. A similar graph you could take for the whole country. So 260 million nodes and edges between friends. And the question for that graph is, how many steps does it take to get from anybody to anybody? And what 2 people are furthest apart in this friendship graph? Say for the
Oh, I know. Fucking Kim Jong-un and... Bro, not even... I know a crazy uncle of mine who has like 0 friends. So he might be one of the candidates for these, you know. I'm thinking like some crackhead from Detroit, Michigan, and my uncle has like the farthest away node. As a matter of fact, it shouldn't even be someone I know, right? If I'm calling him an uncle, that means we have some sort of friendship, some sort of connection. So it's got to be some bum from rural India connected to some first world motherfucker, you know. Third world may connect, you know, because a lot of people from third world have other third world friends, move to other third world, but first world is kind of difficult. That's what I think.
By furthest apart, I mean the distance from, well, I'll tell you my distance to Clinton. It's 2. I happen to go to college with somebody who knows Clinton. I don't know. So my distance to Clinton is not 1, because I don't, happily or not, don't know him. But I know somebody who does. He's a senator, and so I presume you know. Okay, I don't know what's your distance to Clinton? Well, not more than 3, right. Actually, it's true. You know me. I take credit for reducing your Clinton distance. What's your distance to Hanukkah? Not, anybody below 4 is in trouble here. Or maybe 3, but, right. So, what's Hillary's distance to Monica? I don't think you better put that on the page here. 1 or 2, I guess. Is that right? Well, we won't think more about that. So, actually, the real question is, what are large distances? How far apart should people be separated? And roughly, this number 6 degrees of separation has kind of appeared as a movie title, as a book title, and it's with this meaning. That roughly speaking, 6 might be a fairly, not too many people. If you sit next to somebody on an airplane, you get talking to them, you begin to discuss mutual friends to sort of find out, okay, what connections do you have? And very often you'll find you're connected in like 2 or 3 or 4 steps, and you remark it's a small world, and that's how this expression small world came up. But 6,
Whoa.
I don't know if you would successfully discover those 6 in an airplane conversation. But here's the math question, and I'll leave it for next lecture 12, and do a lot of linear algebra lecture 12. But the interesting point is that with a few shortcuts, the distances come down dramatically. All your distances to Clinton immediately drop to 3 by taking linear algebra. That's like the extra bonus for taking linear algebra. And to understand mathematically what it is about these graphs, or like the graph of the World Wide Web, there's a fantastic graph. So many people would like to understand and model the web. What are where the edges are linked and the nodes are websites. I'll leave you with that graph. And see you. Have a good weekend, and see you on Monday.
You gotta see the first couple of... Bro, this shit is like legendary. You know what I mean? The first lecture, look at how many people are there.
And I'm the syllabus for the course.
There's like a lot of people, man, in the first couple of classes. I remember seeing a lot of people on the front row.
The following The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional
Nope. Nope. We ain't doing that. We ain't doing that. Gilbert Strand, a good friend of mine. I'm not donating money to your fund. Whatever.
The following content is provided under a Creative
Oh, bro, I just want to see the students coming in. Bro, look at them. Look at them people, bro. Lot of people. Big ass boats are like, how the fuck are you supposed to like look at what's going on there when you're like 30 or 40 seats back? Impossible. Let's go to this one. This is going to be an interesting one, I think. We'll save this one for the last. We'll do this and some graph questions side by side. I think orthogonal. This is going to be. Let's just actually like look at this. What is going to be pain in the ass? What is going to be really fun? I think I don't like the sound of it. Nah. Projection into onto subspace. Maybe. Projection matrix and least squares. Nah. Orthogonal matrix. Nah. Properties of determinants. Maybe. Determinants, formulas, and cofactors. Maybe. This. Yeah. Yep. Eigen is like fun. I'm really interested. Again, just when I hit the eigen vectors. Alright. And diagonal powers of A. It's kind of interesting. Yeah, that just when I come here, I'm gonna quit. Yeah, matter of fact, yeah. After Unit 2, I'm quitting linear algebra for good. It's been fun. I understand the world better now, but it's gotta go. I gotta learn some differential equation and multivariable calculus and probability. Lot of them. Lot of probability. Yeah, I don't think I need the applications. Maybe if I'm like really bored, I might like take it. That's the thing, like Unit 1 is the biggest one, isn't it? 1, 2, 3, 4, 5, 6, 7. It's like 13 of them, isn't it? 13 or 14. Oh, 12. Yeah, 12. Obviously 12. Obviously it's 12. One, two, three, four. Okay, let's how should be like 11, I think. 11 or 12. Yeah, 12. This is 9. Cool. Unit 3 is the most useless for me, but it's the shortest. Bro, I'm actually like really proud that I'm making this much progress really quick. Yeah, I'm just gonna watch this combined with some neat code problems. I'm gonna eat my lunch while doing it. Cheeky little weight over there. Ooh. No one can disturb me. Yeah. Ooh. Is anyone in here? No one can disturb me. Yeah. Ooh. Is anyone in here? Yeah, this is gonna be a long stream. Be ready. It's gonna be a 10-hour stream. Hopefully not. Give me a second though. I need to contact some people. Sorry guys, I'm just watching Instagram. Yeah. Fuck, what's the plan? In an hour and a half, I need to go. I need to go. Fuck. I'm gonna do that, and I'm just watching Instagram reels. Fuck, I'm wasting time. I'm wasting time in a stream. What if some guy just comes up with a stream? I'm just watching Instagram reels. Fuck, I'm wasting time. I'm wasting time in a stream. What if some guy just comes up with a stream? Okay. What should I do? Should I go back to? Yeah, fuck it. I'm gonna graphs networks. Make a start on. Yeah, fuck it, bro. Just ball. How about this angle? Is it good? How about this? Bald spot? Not even bald, man. I just realized how small it all looks. It looks big for me, but it looks tiny.
Okay, this is lecture 12. We've reached 12 lectures, and this one is more than the others about applications of linear algebra. And I'll confess, when I'm giving you examples of the null space and the row space, I create a little matrix. You probably see that I just invent that matrix as I'm going. And I feel a little guilty about it, because the truth is that real linear algebra uses matrices that come from somewhere. They're not just like randomly invented by the instructor. They come from applications, they have a definite structure, and anybody who works with them uses that structure. I'll just report, like this weekend I was at an event with chemistry professors. Okay, those guys are row-reducing matrices, and what matrices are they working with? Well, their little matrices tell them how much of each element goes into or each molecule, how many molecules of each go into a reaction, and what comes out. And by row reduction, they get a clearer picture of a complicated, how much of each. Okay, those guys are row reducing matrices. And what matrices are they working with? Well, their little matrices tell them how much of each element goes into the, or each molecule, how many molecules of each go into a reaction and what comes out. And by row reduction, they get a clearer picture of a complicated reaction. And this weekend, I'm going to the to a sort of birthday party at MathWorks. So MathWorks is out Route 9 in Natick. That's where MATLAB is created. It's a very, very successful software, tremendously successful. And the conference will be about how linear algebra is used. And so I feel better today to talk about what I think is the most important model in applied math. And the discrete version is a graph. So can I draw a graph, write down the matrix that's associated with it, and that's a great source of matrices. You'll see. So a graph is just, so a graph, to repeat, has nodes and edges. Okay, and I'm going to write down the graph, a graph, so I'm just creating a small graph here. As I mentioned last time, we would be very interested in the graph of all websites, or the graph of all telephones, or the graph of all people in the world. Here, let me take just maybe nodes 1, 2, 3. Well, I better I'll put in that edge, and maybe an edge to a node 4, and another edge to node 4. How's that? So there's a graph with 4 nodes. So n will be 4 in my n equal 4 nodes. And the matrix will have m equal the number, there'll be a row for every edge. So I've got 1, 2, 3, 4, 5 edges. So that will be the number of rows. And I have to write down the matrix that I want to study, I need to give a direction to every edge. So I know a plus and a minus direction. So I just do that with an arrow. Say from 1 to 2, 1 to 3, 2 to 3, 1 to 4, 3 to 4. That just tells me if I have current flowing on these edges, then I know whether it's counted as positive or negative according to whether it's with the arrow or against the arrow. But I just drew those arrows arbitrarily. Okay, because my example is going to come, the example the words that I will use will be words like potential.
Okay, ಮೊದಲ graph, nodes, application in ML and AI. It is a big deal in machine learning and AI because many real world systems are naturally networks, step by step. Fuck, don't do that. We have all these like nodes, tiny, ching, 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 and all of them are connected with arrows, of course, because when it goes this side, it's positive. When it goes the other way, it's negative. Ching, bling, ching, ding, ding. Okay. And yeah, social network, natural language process, sentence or dependency graph, words, syntax, relation, edges, knowledge enhanced language models using graph embeddings to improve context understanding, relation extraction with GNNs, computer vision, image. Will I need I want to use do a YOLO project. You look only linear algebra, matrix multiplication, eigenvectors. What is a tensor? Yeah, guys, like don't rely on AI, obviously. Calculus needed for training the model derivative. Should I? That's a cool idea. Using Eurotunnel as a detect position. For this position, you need more applied computer vision. I mean, ML engineering, space not research. It means medium depth. You don't need to eigenproofs or SVD theory, calculus, little bit depth, medium depth. Okay, practical depth, obviously. Optimization light to medium. Bro, I'm gonna do this. This is the grander plan. Can you guys see this? Is it inverted? No? Fuck, it's inverted. Yeah, it's fucking inverted. I don't give a fuck. Yeah, that's the grand vision. I want to do a BJJ model. A Tinder algorithm, a ChatGPT wrapper. And yeah, that's it. I mean, what else is there, right? I'm gonna take a eating break. I'm gonna eat in the stream, right? It's gonna be our first stream learning. I'm gonna eat in it. I had to. This is the third. Okay. Just need to. Fuck. What am I gonna do? Okay. Where was I? I'm gonna watch some conceptual stuff while I eat because I can't really like do some deep thinking when I'm fucking munching food. Okay. Where was I? I'm gonna watch some conceptual stuff while I eat because I can't really like do some deep thinking when I'm fucking munching food. Fuck. Hate it. Hate when that happens. Okay, back to. I'm gonna watch my favorite YouTuber. Simulating and understanding face. Let's see. Oh, I love chess. Look, let's see. Almost impossible chess puzzle. What is it?
So on each one of the squares, I want to ask what makes people engage with it.
I don't want to do physics, bro. Physics. You fucking puzzles with beautiful solutions. I don't care. Neural networks. Calculus. Okay. Let's look into some calculus. Yeah, what's so special about this number? I'm gonna be making stupid jokes while I eat.
I've introduced a few derivative formulas, but a really important one that I left out was exponentials. So here, I want to talk about the derivatives of functions like 2 to the x, 7 to the x, and also to show why e to the x is arguably the most important of the exponentials. First of all, to get an intuition, let's just focus on the function 2 to the x. And let's think of that input as a time, t, maybe in days, and the output, 2 to the t, as a population size, perhaps of a particularly fertile band.
I think, what was it? The Chernobyl explosion, it was exponentially like fucking up people's radiation or some shit. Something like that. The radiation was exponentially getting larger every single day, and everyone was like dropping dead like flies. Crazy. But the thing is, I remember watching a news channel talking about how COVID is exponentially getting bigger. Probably wasn't true. Exponentially means the human brain couldn't like comprehend what exponential means actually, right? But now we'll turn there. This pen increases twice the rate. Fuck. Your brain can like understand, like, okay, this shit like increases twice. But if I say this is gonna get exponentially bigger, there's like no way you can like understand it.
And of pi creatures, which doubles every single day. And actually, instead of population size, which grows in discrete little jumps with each new baby pi creature, maybe let's think of 2 to the t as the total mass of the population. I think that better reflects the continuity of this function, don't you? So, for example, at time t equals 0, the total mass is 2 to the 0 equals 1 for the mass of one creature. At t equals 1 day, the population has grown to 2 to the 1 equals 2 creature masses. At day t equals 2, it's t squared, or 4, and in general, it just keeps doubling every day. For the derivative, we want dm dt, the rate at which this population mass is growing, thought of as a tiny change in the mass divided by a tiny change in time. And let's start by thinking of the rate of change over a full day, say between day 3 and day 4. Well, in this case, it grows from 8 to 16, so that's 8 new creature masses added over the course of one day. And notice, that rate of growth equals the population size at the start of the day. Between day 4 and day 5, it grows from 16 to 32, so that's a rate of 16 new creature masses per day, which again equals the population size at the start of the day. And in general, this rate of growth over a full day equals the population size at the start of that day. So it might be tempting to say that this means the derivative of 2 to the t equals itself, that the rate of change of this function at a given time t is equal to, well, the value of that function. And this is definitely in the right direction, but it's not quite correct. What we're doing here is making comparisons over a full day, considering the difference between 2 to the t plus 1 and 2 to the t. But for the derivative, we need to ask what happens for smaller and smaller changes. What's the growth over the course of a tenth of a day, a hundredth of a day, 1/1 billionth of a day? This is why I had us think of the function as representing population mass, since it makes sense to ask about a tiny change in mass over a tiny fraction of a day, but it doesn't make as much sense to ask about the tiny change in a discrete population size per second. More abstractly, for a tiny change in time, dt, we want to understand the difference between 2 to the t
It's
plus
like it's like, you know, when like you don't like really feel like you've grown on a day-to-day basis, but if you take like 10 years, right, from the age 10 to like 20, you look back at it and you're like, fuck, I used to be like 4'1", and now I'm like the majestic 6'3". I'm sorry, majestic 5'3". I've grown a lot. You know, I used to be like really short. Now I'm like 5'3". I'm really big now. So yeah, it depends. You know, like if you look at from age 13, if you go back to age 13 and you measure your height for like a month, you wouldn't like see that much difference. But if you go to age 13 to 14, you would be like, oh shit, I've grown like a couple of inches. So that's the idea. Like day to day, it doesn't look really change, but when you take a bigger sample size, it massively changes
dt
things.
and 2 to the t, all divided by dt. The change in the function per unit time, but now we're looking very narrowly around a given point in time, rather than over the course of a full day.
Yes, basically, you know how we like squish us in. Think of the bottom. Think of this thing as like a year. Yeah. Like the years. Fuck, I can't write. Now, if you look at this, the way he shows, fucking hell, bro. Can I just?
time. Rather
The more it squishes smaller, the more less changes you can actually see.
than over the course of a full day. And here's the thing. I would love if there was some very clear geometric picture that made everything that's about to follow just pop out. Some diagram where you could point
That is machine learning at its heart. Just trying to predict the yellow bits over there. That's what we're trying to do.
to one value and say, see, that part, that is the derivative of 2 to the t. And if you know of one, please let me know. And while the goal here, as with the rest of the series, is to maintain a playful spirit of discovery, the type of play that follows will have more to do with finding numerical patterns rather than visual ones. So start by just taking a very close look at this term, 2 to the t plus dt.
I want to ask another question.
A core property of exponentials is that you can break this up as 2 to the t times 2 to the dt. That really is the most important property of exponents. If you add two values in that exponent, you can break up the output as a product of some kind. This is what lets you relate additive ideas, things like tiny steps in time, to multiplicative ideas, things like rates and ratios. I mean, just look at what happens here. After that move, we can factor out the term 2 to the t, which is now just multiplied by 2 to the dt minus 1, all divided by dt. And remember, the derivative of 2 to the t is whatever this whole expression approaches as dt approaches 0. And at first glance, that might seem like an unimportant manipulation. But a tremendously important fact is that this term on the right, where all of the dt stuff lives, is completely separate from the t term itself. It doesn't depend on the actual time where we started. You can go off to a calculator and plug in very small values for dt here. For example, maybe typing in 2 to the 0.001 minus 1 divided by 0.001. What you'll find is that for smaller and smaller choices of dt, this value approaches a very specific number, around 0.6931. Don't worry if that number seems mysterious. The central point is that this is some kind of constant. Unlike derivatives of other functions, all of the stuff that depends on dt is separate from the value of t itself. So the derivative of 2 to the t is just itself, but multiplied by some constant. And that should kind of make sense, because earlier it felt like the derivative for 2 to the t should be itself, at least when we were looking at changes over the course of a full day. And evidently, the rate of change for this function over much smaller time...
This is just talking about exponentially. It's getting doubled. It's like a virus getting doubled exponentially twice. So it could be 3, it could be 4. Doesn't really matter.
Scales is not quite equal to itself, but it's proportional to itself, with this very peculiar proportionality constant of 0.6931.
Oh.
And there's not too much special about the number.
That's just the slope. Y is equal to mx plus c. So yeah, the slope never changes. Kinda. That's kinda true. I mean, it changes the orientation, but the magnitude never changes, I think.
For 2 here. If instead we had dealt with the function 3 to the t, the exponential property would also have led us to the conclusion that the derivative of 3 to the t is proportional to itself. But this time it would have had a proportionality constant 1.0986. And for other bases to your exponent, you can have fun trying to see what the various proportionality constants are, maybe seeing if you can find a pattern in them. For example, if you plug in...
Guys, I think I'm camera shy. I can't really like eat. Yeah, I'm gonna put it in the fridge. Sorry. Sorry, Mom. Let's look into some real shit, bro. None of this like bitch ass. Oh, you guys didn't even see the video. Okay, whatever. I was watching a 3 blue 1 brown video. Hope you guys enjoyed the audio. Yo, so you guys just, yeah, okay, whatever. It was a mukbang. It was a really interesting mukbang, but yo, look at this guy though. Look at this guy. Slay. Look at this guy. I'm gonna whoop your ass the next time I see you, bro. What are you looking at? What are you looking at, huh? You bitch ass. Fuck you up. Pa. 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 That's what I'm saying. Yo, free Diddy. What am I looking at? That's gay. That's gay. That's gay. Gay, gay, gay. Gay boy.
The action principle roughly states that nature wants to minimize.
What? I mean, I really admire these guys, bro. They're fucking Euler's. Yeah, what even? I think the sigmoid function is sigmoid function. Not quite. Yeah, it uses a Euler number, Euler's number. So apparently, Euler was like a blind guy too, which is, bro, you do you, bro. I ain't trying to be blind and do math. You know what I mean? Like being like I can see things clearly. Still, math is like, what am I even looking at half the time? Lie groups, algebras, brackets, differential geometry. Okay, let's try it. You know? What's the worst thing that can happen? Quantum mechanics. Interesting. Complex analysis.
Hey, can you cover complex analysis?
Machine learning, or what else? What's the another thing? So it is important to know this. Yeah, it's a new concept. I don't even know what complex analysis mean. Essence of group theory, mathematics of corona. Whoa! I thought the COVID virus was a lie, guys. What the fuck? Oh, it's real. Geometry gem.
We first learned that finding
Yeah, bro. Why didn't, bro? Some of these videos, I wish I had it when I was like studying math when I was a kid. It used to piss me off studying mathematics in a unrealistic way. I'm just gonna get some water. I have a mild cold. You know, usually I don't get sick. I never get sick, honestly. Yeah. Yeah, just keep this somewhere. I got some coffee, water. Tick, tick, tick. I need to set up an alarm. Ugh. What the fuck? Enjoying the coffee? Bro, why does my clock need an update? So, come on. In an hour. In an hour, I'll be. Bye bye. Bro, what the fuck am I even looking, bro? You mean? Can I just edit it? Like, what am I? Wow. Look at that. What are you gonna do? Wow, you did nothing. How do you feel about that? How do you feel about that, bro? You did absolutely nothing. Wow. It's actually crazy. It's actually crazy how smart you are. Okay, I gotta use my phone. Again, an hour, I'm out. Hopefully. Fuck. Fuck's sake. Please. Thank you. Thank you. How much? How long is it? The Gilbert Strand. Can I do it in an hour? Probably.
Okay, this is lecture 12. We've reached 12 lectures, and this one is more than the others about applications of linear algebra. And I'll confess, when I'm giving you examples of the null space and the row space, I create a little matrix. You probably see that I just invent that matrix as I'm going. And I feel the discrete version is a graph. So can I draw a graph, write down the matrix that's associated with it, and that's a great source. So that will be the number of rows. And I have to write down the matrix that I want to study. I need to give a direction to every edge, so I know a plus and a minus direction. So I just do that with an arrow. Say from 1 to 2, 1 to 3, 2 to 3, 1 to 4, 3 to 4. That just tells me if I have current flowing on these edges, then I know whether it's counted as positive or negative according to whether it's with the arrow or against the arrow. But I just drew those arrows arbitrarily. Okay, because my example is going to come, the words that I will use will be words like potential, potential difference, currents. In other words, I'm thinking of an electrical network. But that's just one possibility. My applied math class builds on this example. It could be a hydraulic network, so we could be doing flow of water, flow of oil. Other examples, this could be a structure, like a design for a bridge or a design for a Buckminster Fuller dome, or many other ones. So many. But let's take potentials and currents as a basic example, and let me create the matrix that tells you exactly what the graph tells you. So now I'll call it the incidence matrix. Incidence matrix. Okay, so let me write it down and you'll see what its properties are. So every row corresponds to an edge. I have 5 rows from 5 edges, and let me write down again what this graph looks like. Okay, the first edge, edge 1, goes from node 1 to 2. So I'm going to put in a -1 and a +1 in, this corresponds to node 1, 2, 3, and 4, the 4 columns. The 5 rows correspond, the first row corresponds to edge 1. Edge 1 leaves node 1 and goes into node 2, and it doesn't touch 3 and 4. Edge 2. Edge 2 goes, oh, I haven't numbered these edges. I just figured that was probably edge 1, but I didn't say so. Let me take that to be edge 1. Let me take this to be edge 2. Let me take this to be edge 3. This is edge 4. Oh, I'm discovering, no, wait a minute. Did I number that twice? Here's edge 4, and here's edge 5, okay? All right. So edge 1, as I said, goes from node 1 to 2. Edge 2 goes from 2 to 3, node 2 to 3, so -1
What
and
the
1
fuck?
in the second and third column. Edge 3 goes from 1 to 3. I'm tempted to stop for a moment with those 3 edges. Edges 1, 2, 3. Those form what do you call the subgraph formed by edges 1, 2, and 3? That's a loop. And the number of loops and the position of the loops will be crucial. Okay. Actually, here's an interesting point about loops. If I look at those rows corresponding to edges 1, 2, 3, and these guys made a loop, you want to tell me, if I just looked at that much of the matrix, it would be natural for me to ask, are those rows independent? Are the rows independent? And can you tell from looking at that if they are or are not independent? Do you see a relation between those 3 rows? Yes. If I add that row to that row, I get this row. So that's like a hint here, that loops correspond to linearly dependent columns, linearly dependent rows. Okay, let me complete the incidence matrix. Number 4, edge 4 is going from node 1 to node 4. And the 5th edge is going from node 3 to node 4. Okay, there's my matrix. Came from the 5 edges and the 4 nodes. And if I had a big graph, I'd have a big matrix. And what questions do I ask about matrices? Here's the review now. There's a matrix that comes from somewhere. If it was a big graph, it would be a large matrix, but a lot of zeros, right? Because every row only has 2 non-zeros. So it's a very sparse matrix. The number of non-zeros is exactly 2 times 5. It's 2m. Every row only has 2 non-zeros, and that's with a lot of structure. And that was the point I wanted to begin with. That real graphs from real matrices, from genuine problems, have structure. Okay. We can ask, and because of the structure, we can answer the main questions about matrices. So, first question, what about the null space? So what am I asking? If I ask you for the null space of that matrix, I'm asking you if I'm looking at the columns of the matrix, 4 columns, and I'm asking you, are those columns independent? If the columns are independent, then what's in the null space? Only the 0 vector, right? The null space tells us what combinations of the columns, it tells us how to combine columns to get 0. And is there anything in the null space of this matrix other than just the 0 vector? In other words, are those 4 columns independent or dependent? Okay, so that's our question. Let me, I don't know if you see the answer. Whether there's, let's see, I guess we could do it properly. We could solve AX equals 0. So let me solve AX equals 0 to find the null space. Okay, what's AX? Can I put X in here in little letters? X1, X2, X3, X4. It's got 4 columns. AX now is that matrix times X. And what do I get for AX? If the camera can keep that matrix multiplication there, I'll put the answer here. AX equal, what's the first component of AX? Can you take that first row, -1, 1, 0, 0, and multiply by the X, and of course you get X2 minus X1. The second row, I get X3 minus X2. From the third row, I get X3 minus X1. From the fourth row, I get X4 minus X1. And from the 5th row, I get X4 minus X3. And I want to know, when is the thing 0? This is my equation, AX equals 0. Notice what that matrix A is doing. We've created a matrix that computes the differences across every edge. The differences in potential. Let me even begin to give this interpretation. I'm going to think of this vector X, which is X1, X2, X3, X4, as the potentials at the nodes. So I'm introducing a word, potentials at the nodes. And now if I multiply by A, I get these 5 components, X2 minus X1, etc.
Yeah.
And what are they? They're potential differences. That's what A computes. If I have potentials at the nodes and I multiply by A, it gives me the potential differences, the differences in potential across the edges. Okay.
Ah.
When are those differences all 0? So I'm looking for the null space. Of course, if all the x's are 0, then I get 0. That just tells me, of course, there's 0 vectors in the null space. But there's more in the null space. Those columns of A are dependent, right? Because I can find solutions to that equation. Tell me the null space. Tell me one vector in the null space. So tell me an x. It's got 4 components, and it makes that thing 0. So what's a good x to do that? 1, 1, 1, 1. Constant potential. If the potentials are constant, then all the potential differences are 0, and that x is in the null space. What else is in the null space? Yeah, let me ask you this always. Give me a basis for the null space. A basis for the null space will be just that. That's it. That's a basis for the null space. The null space is actually one-dimensional, and it's the line of all vectors through that one. So there's a basis for it, and here's the whole null space. Any multiple of 1, 1, 1, 1 is the whole line in 4-dimensional space. You see that that's the null space. So the dimension of the null space of A is 1. And there's a basis for it, and there's everything that's in it. Good. And what does that mean physically? I mean, what does that mean in the application, that guy in the null space? It means that the potentials can only be determined up to a constant. Potential differences are what make currents flow. That's what makes things happen. It's these potential differences that will make something move in our network between node 2 and node 1. Nothing will move if all potentials are the same. If all potentials are C, 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 and C, then nothing will move. So we have this one parameter, this arbitrary constant that raises or drops all the potentials. It's like ranking football teams, whatever. There's a constant, or looking at temperatures. There's a flow of heat.
I don't give a fuck, bro. Don't give a fuck about potential. Don't give a fuck.
From higher temperature to lower temperature. If temperatures are equal, there's no flow, and therefore we can measure temperatures. We can measure temperatures by Celsius, or we can start at absolute 0. And that it's the same arbitrary constant that was there in calculus. In calculus, right, when you took the indefinite integral, there was a plus C. And you had to set a starting point to know what that C was. So here what often happens is, we fix one of the potentials like the last one. So a typical thing would be to ground that node, to set its potential at 0. And if we do that, if we fix that potential so it's not unknown anymore, then that column disappears, and we have 3 columns, and those 3 columns are independent. So I'll leave the column in there, but we'll remember that grounding a node is the way to get it out. And grounding a node is the way to setting a potential to 0 tells us the base for all potentials, then we can compute the others. Okay, but now I've talked enough to ask what the rank of the matrix is. What's the rank then? The rank of the matrix, so we have a 5x4 matrix. We've located its null space, one-dimensional. How many independent columns do we have? What's the rank? It's 3. And the first 3 columns, or actually any 3 columns, will be independent. Any 3 potentials are independent good variables. The 4th potential is not. We need to set, and typically we ground that node. Okay, rank is 3. Rank equals 3. Okay. Let's see, do I want to ask you about the column space? The column space is all combinations of those columns. I could say more about it than I will. Let me go to the null space of A transpose. But the equation A transpose Y equals 0 is probably the most fundamental equation of applied mathematics. Let's talk about that. That deserves our attention. A transpose Y equals 0. That's when you put it on there. Okay. So A transpose Y equals 0. So now I'm finding the null space of A transpose. Oh, and if I ask you its dimension, you could tell me what it is. What's the dimension of the null space of A transpose? We now know enough to answer that question.
What is the null space? N minus R.
What's the general formula for the dimension of the null space of A transpose? A transpose, let me even write out A transpose, is A transpose will be n by m, right? N by m. In this case, it'll be 4 by 5.
Yeah,
Those
okay.
columns will become rows.
M minus
0,
M
minus
minus
1,
R.
minus 1, 0 is now the first row. The second row of the matrix, 1, minus 1, and 3 zeros. The third column now becomes the third row, 0, 1, 1, 0, minus 1. And the fourth column becomes the fourth row. Okay, good. There's A transpose. That multiplies Y. Y1, Y2, Y3, Y4, and Y5. Okay, now you've had time to think about this question. What's the dimension of the null space? If I set all those, wow. Usually, sometime during this semester, I'll drop one of these erasers behind there. That's a great moment. There's no recovery. There's centuries of erasers are back there. Okay. Okay, what's the dimension of the null space? Give me the general formula first in terms of R and M and N. This is like crucial. We struggled to decide what dimension meant, and then we figured out what it equaled for an M by N matrix at rank R, and the answer was M minus R, right? There are M equal 5 components, M equal 5 columns of A transpose, and R of those columns are pivot columns, because they'll have R pivots that has rank R, and M minus R are the free ones now for A transpose, so that's 5 minus 3, so that's 2. And I would like to find this null space. I know its dimension. Now I want to find out a basis for it. And I want to understand what this equation is. So let me say what A transpose Y actually represents. Why I'm interested in that equation. Yeah, I'll put it down with those old erasers and continue this. Here's the great picture of applied mathematics. So let me complete that. There's a matrix that I'll call C that connects potential differences to currents. So I'll call these are currents on the edges. Y1, Y2, Y3, Y4, and Y5. Those are currents on the edges. And this relation between current and potential difference is Ohm's law. This here is Ohm's law. Ohm's law says that the current on an edge is some number times the potential drop. And that number is the conductance, 1 over the resistance. This is the old current is the relation of current, resistance, and change in potential. So it's a change in potential that makes some current happen. And it's Ohm's law that says how much current. And that's, what does that say? It has a famous name. It's Kirchhoff's current law, KCL. Kirchhoff's current law, A transpose Y equals 0. So that when I'm solving, when I go back up with this blackboard and solve A transpose Y equals 0, it's this pattern that I want you to see. That we had rectangular matrices and real applications. But in those real applications comes A and A transpose. So our 4 subspaces are exactly the right things to know about. All right, let's know about that null space of A transpose. Wait a minute, where'd it go? Here it is. Okay. Null space of A transpose. We know what its dimension should be. Let's find out. Tell me a vector in it. Tell me, now, so what am I asking you? I'm asking you for 5 currents that satisfy Kirchhoff's current law. So we better understand what that law says. That law, A transpose Y equals 0. What does that say? Say in the first row of A transpose, that says, so the first row of A transpose says minus Y1 minus Y3
second row.
minus Y4 is 0. Where did that equation come from? I'll redraw the graph. Can I redraw the graph here so that we see again there was node 1, node 2, node 3, and then a Y2. It's been telling me. This first equation of Kirchhoff's current law. What does that mean for that graph? Well, I see
It's,
Y1, Y3,
negative.
and Y4 as the current leaving node 1. So sure enough, the first equation refers to node 1, and what does it say? It says that the net flow is 0. That equation, A transpose Y, Kirchhoff's current law, is a balance equation, a conservation law. Physicists be overjoyed by this stuff. It says that in equals out. And in this case, the 3 arrows are all going out, so it says Y1, Y3, and Y4 add to 0. Let's take the next one. The second row is Y1 minus Y2, and that's all that's in that row, and that must have something to do with node 2. And sure enough, it says Y1 equals Y2, current in equals current out. The third one, Y2 plus Y coming in. That at this node, at near algebra, but this matrix, A transpose, by looking at the graph and the special matrix we're going to have studied earlier, what's the null space, all the information, what are the dependencies? We'll find those by elimination, but here, in a real example, we can find them by thinking. Okay. Again, my question is, what is a solution Y? How could current travel around this network without collecting any charge at the nodes? Tell me a Y. Okay. So a basis for the null space of A transpose. How many vectors am I looking for? 2. It's a 2-dimensional space. My basis should have 2 vectors in it. Give me 1. One set of currents. Suppose, let me start it. Let me start with Y1 as 1. Okay, so 1 unit of 1 amp travels on edge 1 with the arrow. Okay, then what? What is Y2? It's 1 also, right? And of course, what you did was solve Kirchhoff's current law quickly in the second equation. Okay, now we've got 1 amp leaving node 1, coming around to node 3. What shall we do now? Well, what shall I take for Y3? Well, I've got a choice, but why not make it, what you said, -1? So I've just sent current 1 amp around that loop. What shall Y4 and Y5 be in this case?
My fucking bitch ass neighbor just walked in. Fuck you up. Pop, pop, pop. Pop.
We could take them to be 0. This satisfies Kirchhoff.
Actually, don't mind. Don't mind though. A little bit annoying, but it is what it
Current law.
is. You know?
We could check it patiently, that minus Y1 minus Y3 gives 0. We know Y1 is Y2. The other is Y4 plus Y5 is certainly 0. Any current around a loop satisfies the current law. Okay, now you know how to get another. Take current around this loop. So now let Y3 be 1, Y5 be 1, and Y4 be minus 1. And so we have the first basis vector sends current around that loop. The second basis vector sends current around that loop. And those are independent. And I've got 2 solutions, 2 vectors in the null space of A transpose, 2 solutions to Kirchhoff's current law. Of course, you would say, what about sending current around the big loop? What about that?
Okay, I don't care.
One
I don't care
for
about
Y1,
currents.
1 for Y2, nothing on Y3, 1 for Y5, and minus 1 for Y4. What about the first column plus the second column equals is at this formula, the dimension of the null space of A transpose is M minus R. Okay. This is the number of loops, number of independent loops. M is the number of edges. And what is R? What is R for our, we'll have to remember way back. The rank came from looking at the columns of our matrix. So what's the rank? Let's just remember. Rank was, you remember there was one, we had a one-dimensional multiple. The rank was n minus 1. That's what I'm struggling to say. Minus the number of edges. Plus the number of loops. Is, the rank came from looking at the columns of our matrix. So what's the rank? Let's just remember. Rank
Edges
was
minus.
we had a one-dimensional multiple. The rank was n minus 1. That's what I'm struggling to say. Because there were n columns coming from the n nodes. So it's minus,
Edges minus
the number of nodes
nodes.
minus 1. Because of that C, that 1, 1, 1, 1 vector in the null space, the columns were not independent. There was one dependency, so we needed n minus 1. This is a great formula. This is like the first. Shall I write it slightly
Nodes
differently?
minus 1.
The number of edges. Let me put things. Have I got it right?
So let's say ஒரு loop இருக்கு நம்ம அது pam pam pam. Why is it always got to be a triangle, man? What are they coming to say us? Okay. Goes toing, showing, showing. Minus 1, plus 1. I would whoop your ass, bro. Whoop your ass. Fuck. Okay. If I look at, yeah, I need to like beat up some of these black belts, bro. I want to fuck all of these guys up.
Number of edges is m. The number is m minus r. Okay, so I'm getting. Let me put the number of nodes on the other side. Right, the number of nodes. I'll move that to the other side. Minus the number of edges. Plus the number of loops. Is, I have minus 1 is 1. The number of nodes minus the number of edges plus the number of loops is 1. These are like zero-dimensional guys. They're the points on the graph. The edges are like one-dimensional things. They connect nodes. The loops are like two-dimensional things. They have like an area. And this count works for every graph. And it's known as Euler's formula. We see Euler again. That guy never stopped. Okay. And can we just check? So what am I saying? I'm saying that linear algebra proves Euler's formula. Euler's formula is this great topology fact about any graph. Let me draw another graph. Let me draw a graph with more edges and loops. Let me put in lots of. Okay, I just drew a graph there. So what are the quantities in that formula? How many nodes have I got? Looks like 5. How many edges have I got? 1, 2, 3, 4, 5, 6, 7. How many loops have I got? 1, 2, 3. And Euler's right. I always get 1. This formula is extremely useful in understanding the relation of these quantities: the number of nodes, the number of edges, and the number of loops.
Interesting.
Okay, I'll just complete this lecture by completing this picture, this site. So let me come to the so this expresses the equations of applied math. Let me call these potential differences, say E. So E is AX. That's the equation for this step. The currents come from the potential differences. Y is CE. I'm just going to put these three equations together. So I start with X, my unknown, E, and now I have applied math. Coming from these three steps, in which the last step is this balance equation. There's always a balance equation to look for. These are when I say the most basic equations of applied mathematics, I should say in equilibrium. Time isn't in this problem. Newton's law isn't active here. I'm looking at the equations when everything is settled down. How do the currents distribute in the network? And A transpose A. It is always symmetric. Right. Okay, thanks. So I'll see you Wednesday for a full review of these chapters, and Friday you get to tell me. Thanks.
Not many people. Not many people on the final lesson. Do I have time for this? I do. Do I want to do it? Not really. How long have I been streaming? Yeah, let's call it a day.